So my name is Jeff McGehee. I'm a data scientist and the IoT practice lead at Very. We are a remote software consultancy. And as a consultancy, we have to operate under this constraint that our client is going to want estimates for our work. And in order to keep them happy, we also need to deliver on those estimates. We can't be dragging things way out beyond what we've said this is going to cost, because they're making decisions based on money and burn down and all of that. So, this estimation problem, it's what we do as data scientists. And it's inherently a prediction problem. It's not super easy for even general software development. There's a whole school of thought about how to do this effectively for just standard software development. And then even in the world at large, we have the concept of the planning fallacy, and it's difficult to plan anything, and especially as it grows in complexity and starts to include things like machine learning, which in itself is a complex task. So what I'm going to talk about is how we're managing this problem of delivering high-quality machine learning solutions in a predictable manner. And the idea really is, in my opinion, the process that we follow is everything. And this is an argument in favor of Google's rules of machine learning. If you haven't heard of this, or if this isn't something that's familiar to you, take some time and look it up. We've been thinking about this as a team for quite some time, how to do this well, and we discovered these Google's rules of machine learning along the way, identified with a lot of it, and have started to take it seriously and try to follow these rules and adapt them to our own work and that sort of thing. So it's definitely worth taking note of that and thinking about that and realizing that that has a heavy influence on what I'm about to talk about. So in case you haven't really bought into the idea that the process should be a large area of your focus as a data scientist, I'm going to share a little bit of what I'm going to call theory in air quotes, but it's more like a loose framework for reasoning about technical choices and priorities. Our Bayesian friend who just presented, hopefully he would appreciate it. And so hopefully that'll convince you that the development process is very important, especially right now in machine learning. So when building a machine learning application, it's easy, relatively, if you're comfortable with machine learning, to do things like minimize your model loss. But it's relatively hard to maximize the overall value delivered of your system. And as we think about optimization, in order to perform any sort of optimization, we need to have a measure of success. And so if we're thinking about sabermetrics for machine learning engineering, or what sort of stat would we define, or if we're a growth-crazed CEO, what would be the KPI that we're putting on our company report card about, to define how we're doing, right? So, introducing what I'm going to call SOD QWOP. So, it really rolls off the tongue, so I just thought I'd stick with it. And really, what I'm saying that it stands for is speed of delivery and quality of product. So in terms of speed of delivery, we have time to market, but then over time, do you still have the ability to add new features in an agile way? And do you have the ability to pivot based on your market needs? And then on the other side, quality of product. I'm going to make the argument that it really comes down to user experience. Software engineers, they can really talk a lot about what they think quality is, but I'm going to say it's user experience. And we need to have things like reliability, availability, ease of use, and valuable features, which I think this is where the machine learning part comes in, providing valuable features that maybe wouldn't be available elsewhere. And so the appropriate level of seriousness for defining this metric SODQuap, I thought, was this nice LaTeX and emoji combo of an equation, which is basically, I've loosely defined it here as 100 over 1 plus the average days it takes you to develop a new feature times the fraction of satisfied users over the total number of users in your market, right? So it's like pretty easy to reason about. The lower bound is 0, the upper bound is 100. 0 is bad, 100 is good. It's pretty simple to think about. So thinking about it a little deeper, how would this change over time, like for a market or an industry on average? And we would basically expect that companies would increase, an average SODQuap over time, and there would be some convergence, maybe. It's definitely bound by 100, but in general, it's going to be increasing. And however, at any given time, this line represents the average, and so if we have an average, we probably have some distribution at a point in time. And so there's going to be winners pushing forward at any point in time, and there's going to be losers falling behind. And how do we end up on the right side of the distribution at any point in time in terms of this SODQuap metric that we care so much about? And so if we think about a point in time, you may end up in a relatively stagnant era of technology where everyone's real narrow and bunched together, or you may end up somewhere where the distribution is wide and you can sort of take maybe some easier steps to get out ahead. And bear with me, but I'm getting here to this is the way we want to frame these decisions, and then how can we what levers can we pull to make sure that we end up on the right of this distribution? Basically that we're delivering better than anyone else or than most. And so now think of it sort of as like a mixture distribution at any point in time. And you have some latent combination of latent distributions that may make up this mixture. It might be single modal, it might be multimodal in the end, but just keeping it simple here, you have some aggregate mixture, and really on the right is going to be winners, and on the left is going to be losers. So people who are delivering faster and higher quality, and people who aren't meeting that standard, and then there's going to be people in the middle. And we can think about 3 sort of latent distributions that are easy to reason about that might be a part of this mixture are people, tooling, and process. So when you're trying to make decisions, think about your industry in particular or your area of focus where you're trying to make decisions. And in this machine learning area, I'm making some generalizations and assumptions here as a Bayesian might. And the people are sort of going to always roughly be the same. There's going to be low performers and high performers. And you try to pick the high performers, but you may not be able to do that. Tooling, at least right now, it seems like it's all sort of everybody's roughly working with the same set of tools. There may be a paradigm shift coming to other things. Maybe TPUs are going to make a big dent or a big paradigm shift in our tooling. I don't know in particular. But an area that I think really has the highest variance is the process of how people are implementing machine learning solutions in production. And so it's easy to see that if you're on the right side of these latent distributions, you're going to end up on the winning side of the aggregate distribution. So if you think in this way, we can look and see sort of where it's easiest to push towards the right, to how can we differentiate ourselves? And I'm asserting here that I think a big part of this is process. So hopefully, you'll agree with me and realize that process is the place where machine learning application development has the most room for improvement. And because of that high variance, it's probably the easiest place for you to make a change that will have an impact on where you sit in the aggregate distribution. So take that for what it's worth, but that's sort of my argument on why I think this is so important. And hopefully you trust the process if you are any sports fans out there. Okay, so at Very, how are we thinking about this as machine learning engineers? It's not, we try pretty hard to make our process an engineering process and not a research process. I'll talk a little bit more about that. But stakeholders are always losing money as a function of time. So anything we can pull like out of research and into an engineering mindset, we try to do this. And so be an engineer, build lean, be clever with machine learning APIs, and make it easy to improve your model. These are the 4 things that I think that are most important that we're doing. And I'll talk a little bit about each one, sort of in general, what we'd like to see, and then things that we're doing in particular. So scientists make discoveries, right? And they're extremely important. But then the engineer's role is to develop predictable processes for aggregating and leveraging the discoveries sort of in the world at large. And so engineers can do research, but primarily their research is about applying science in a predictable way, right? Like just because we understand mechanics from like a research perspective doesn't mean we know all the processes for building a bridge correctly. That's not going to fail. And so that's where the engineering comes in. So how can we apply this here? And I think in general, we want to be a student of science and research, but we want to focus on finding flexible methods of reliable implementation, like I was talking about, rather than pushing for state-of-the-art in a particular area. And then I sort of already said this already, but don't rely on discoveries in order to ship products. So you don't want to be under the gun on the client's dollar, like banking on making some revolutionary discovery so that you can get a product out the door. It's a really tough place to be in for everyone involved. So just don't do that. Try to build your systems in ways where that's not a need. And so things that we're doing is our machine learning engineers build the entire system. So they prototype the models, they build the production models, and they build the production infrastructure. So they're intimately familiar with all the tooling, simple machine learning models that we can plug in to our architecture, and then once we have a full pipeline, we can swap those out. So we become familiar with like how to do that first part quickly so that something's there. And then if we need to push for greater accuracy, we do that next. And then we study new methods so that leveraging a new tool is not a research endeavor. So we go to conferences, we learn, we study in our free time. Our company gives us some time on the clock to do professional development so that when it comes time and you're under the gun on a client project, you're not doing research. You already know how this works, and you're doing implementation at that point. The next thing, build lean. In general, understand what you're measuring and why. And it's important to note that this could be a side effect of your model, like not your accuracy, however you're choosing to measure accuracy, but something like user engagement. And so you may have a hypothesis that your model accuracy will be correlated with that metric, but you won't really know unless you have shipped a model into production and are starting to make real measurements. So take this, what you're measuring and why, pretty seriously. Fail fast, and then take ship early and ship often seriously. That's sort of, I've touched on this quite a bit, but don't waste time chasing a little bit of accuracy on a feature that you don't even know if users are going to use or maybe they would be satisfied with not great accuracy, and then you could spend your time elsewhere. So yeah, ship and then decide. And then, so things that we're doing, we really try to say 2 weeks or less to validate machine learning as a viable solution for any problem. So we get your data, and then in 2 weeks, I mean, of course, we're not like pushing the state of the art in those 2 weeks, but we're seeing if there's any signal that we can latch onto. Like, is there something here that we're confident that we can deliver value for? And to do that, we use all the tools that most people are using. You saw how I feel the tooling distribution sits right now, super narrow. So, I mean, Jupyter, Pandas, scikit-learn, TensorFlow, Keras, Matplotlib, a lot of the Python stack primarily. And if you haven't failed in those 2 weeks, then ship what you have. And to do that, it's pretty easy, especially with SageMaker. There was a good talk on that from AWS today, to go from prototype to production super quick. And we leverage a lot of the AWS tools. I personally think there's other great tools out there with the other cloud providers, but we at Very use AWS. And then we iterate rapidly as needed. So if we need to iterate, we do. But sometimes, once you're in production, if everything's happy, you just leave it with your logistic regression or whatever you have. This one might be a little controversial because we all like to do things on our own and be fancy and not just query a web endpoint to get an answer. But I think it's critical to being able to move fast and be clever with machine learning APIs or pre-trained models that are out there. Don't reinvent the wheel as an engineer. Yeah, if you're a researcher, fine. Try to push the state of the art. But as an engineer, don't reinvent the wheel. Use these pre-built tools. And here, when you're using a pre-built tool, though, you still need to have a deep understanding of what your accuracy is, and you still need to measure your accuracy on that tool. You can't take for granted the accuracy that something like a facial recognition API is going to provide for you. You have to provide those measurements or measure that on your own with data that's relevant to your problem. And then build custom solutions where they're going to have the highest impact. So if you can reach for something off the shelf, but you have something like in the last talk where you have some optimal decision making that you need to make, maybe that's the place where you need to be spending your time. So just think about that and individually with your problems. And then what we're doing is we like to wrap noisy API models with a Bayesian inference engine. And this is really simple to do. But basically, if you have some noisy predictions coming back from some API, take more measurements, right? I mean, that should be our intuition. Take more measurements, leverage Bayes' rule, essentially, to provide more confident answers. And then you can also obtain features from these models. So instead of trying to do object detection or word to vec or something like that on your own, there's pre-trained implementations out there for you, and then use those as features for more rich and complex systems that you need to build to deliver whatever product your customer needs. And then lastly, make it easy to improve your models. And this is pretty key because, like I've mentioned, we want to ship something that's very simple, maybe not quite at the accuracy level we desire. And if we are going to do that as part of our process, we need to make it easy to update it, to make it better. So in general, and this is stuff that you've probably heard if you're doing some online learning or retraining in production and that sort of thing. But record your predictions along with the ground truth and the inputs if you can. And build software features. So not like machine learning model input features, but actual features in your software, like user-facing features that allow users to label or make corrections on your predictions. It's not that hard to do, and I think a lot of us have intuition, and we've seen this done on products that we use, but it's definitely something worth mentioning. And then collect data that might be leveraged for future models. So if you you may not need to do an optimal decision-making engine around some other predictions, some other noisy predictions like you're making right now, but you might know that you need to do that in the future. So just like be cognizant of that and be collecting that data as you go. And then when it makes sense, facilitate online learning and retraining. Sometimes our customers need something like that, sometimes they don't. And so things that we do, we leverage AWS Lambda to collect a lot of these data related to the model feedback and to trigger training jobs and that sort of thing. We encapsulate models using tools like Docker or SageMaker, or SageMaker has or did have, I hope they still do have support for Docker containers as the model. And you can sort of pass into this model the largest feasible amount of features that you think make sense. And so at that point, and then you can do like the feature reduction within that box so that it's easy to swap out with like something that may leverage features that you're not using right now or something like that. So that's something that we try to do. And then lastly, we're a big proponent. I haven't mentioned it. You might guess since I'm like hounding on this process, but a big proponent of Agile, and we believe in extreme programming and high test coverage. And so I really think high test coverage is important for facilitating agility around your changing model. So, and I'm talking about automated tests, like in terms of unit tests for your software, also in terms of like automated accuracy checks and that sort of thing, so that you know, okay, am I confident that I can ship this? Because if you're going to ship often, you need to be confident when you're doing it. So that is all I have. I'm over time, I think. But if you guys have any questions, feel free to catch me out in the hall. I'd be glad to talk.